The goal today is to graph any secant function and any cosecant function. You've already seen sine and cosine. You've already seen tangent and cotangent. Now, the nice thing about graphing secant is the reciprocal of secant is cosine. So the nice thing is you're going to graph cosine and use cosine as a guide to graph secant. So really, graphing secant is really practicing more cosine. Cosecant, same thing. The reciprocal of cosecant is sine. So you're going to graph a sine function and use it as a guide to graph cosecant. All right, so let's look at the original graph of cosecant. So the cosecant graph is, I call it an inversion of sine. Okay, so for the sake of consistency, I'm going to graph y equals sine of x in orange. Okay, so let me remind you, sine goes through the origin initially, goes up to 1, comes down, hits the x-axis, hits the midline. The midline is what we're going to focus on. Midline, max, midline, minimum, midline, that's one full period. Okay? So just to recap, to graph cosecant, you're really going to graph sine, and we'll do an example, and then you're going to use it as kind of a guiding force. So here's what I know. So now everything else is cosecant. This is really what I'm graphing. So some students will graph the sine function very lightly. I did it in orange. And then graph cosecant bold. Okay? So when I plug in 0, I get out 0. Well, what's the reciprocal of 0? Undefined. Every point on the midline of sine will be a vertical asymptote undefined for cosecant. So what's the once again, what's the reciprocal of an output of 0 for sine? Undefined for cosecant. So every point on the midline of sine represents an undefined value for cosecant. Okay? And then it gets kind of interesting. So if I plug pi over 2 into sine, I get 1. Well, what's the reciprocal of 1? It's just 1. So the beauty is, this point, the maximum value for sine is actually always the minimum value for cosecant. They actually share this point in common. Same thing here. When you plug in a number and get out -1, what's the reciprocal of -1? Well, it's -1. Okay, so at the top, at every hump, that's what I call it, at every hump, every turning point, you're going to have a shared point for sine and cosecant. For every turning point or hump, you're going to have a shared point. All right, now here's the concept. So I really want you guys to understand why you're doing what you're doing, okay? It's because the what you're doing is easy, right? I can teach a third grader, draw a hump and then draw a little bowl on top. Anybody can do that, but I want you guys to understand what you're actually doing. All right, so 1/2. For the sine function, after you get an output of 1 for sine, the y values are going to decrease and approach 0. So your y value here is maybe 0.8 and then 0.7. At some point on this curve, you're going to have an output, a y value of 1/2. And we already know what that is from the unit circle. Well, what's the reciprocal of 1/2? It's going to be 2. All right? So as these y values decrease for sine, the inverse, the reciprocal, is going to blast off to infinity. So think of what's the reciprocal of 1/3? It's 3. What's the reciprocal of 1/4? It's 4. What's the reciprocal of 1/10? It's 10, and so on. So as the y values approach 0, their inverses, their reciprocals, approach infinity. So what I'm sketching here in red, once again, invert all of these smaller numbers and they get larger. Okay, so for every hump of the sine wave function, this is your cosecant function. And they share this point in common. So it's a big deal that they touch right here, that this point is pi over 2, 1 for both functions. So make sure when you use the sine function to sketch cosecant that you actually have that point of contact. Same thing here. Okay? So for those of you who want to graph multiple waves, that's fine. That just means you're going to have to graph a whole lot of hookies, hooky, 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 hooky. On top of every one of those humps, or below every one of those humps, there should be a, what looks almost like a parabola, but it's not a parabola. All right. So let's go back to what you need to show me minimally. All right, so minimally, for sine, you had to have 1, 2, 3, 4, 5 values for a given period on the x-axis. Same for cosecant. All right, for sine, you always had 1, 2, 3 points on the midline. So now you're going to have a minimum of 1, 2, 3 vertical asymptotes. All right. For the sine function, you had a minimum of 1 maximum and 1 minimum. Well, if you have 1 maximum, you should have a curve blasting out and up. And for that minimum value, you should have a curve, a branch. We call this one branch of the function, a second branch of the function. Okay, so if you have 2 humps on your sine, you should have 2 branches or curves with 2 arrows for your cosecant. All right, that's what you would graph. Now let's look at secant. Now secant's a little bit different just because sine was always a nice, if you only graphed one full period, sine was one nice wave, whereas cosine wasn't. Okay, so once again in orange, for secant, you automatically say, okay, well, I'm not graphing secant. I'm going to graph cosine to get a handle on secant. So just to remind you, we started cosine up at 1, and we went down to pi over 2, down to pi, up to 3 pi over 2, and 2 pi. Okay, so my same 5 x values that gave me y values of 1, 0, -1, 3 pi over 2, 2 pi. Now, some of you have been only graphing this because that's all you had to do minimally. I would extend it a little bit to the left. You don't have to. And I would extend it a little bit to the right, only because I'm seeing weird things. I'm seeing like arrows going up from here and arrows going up from here, and you know, that's fine. I don't want you to forget the fact that even though you're graphing this portion of the graph, it does continue after this point and that point to go down. The wave continues. Okay, so just to be clear, minimally, like before, you start at 0, you end at 2 pi. One full wave with exact values in between 5 total. Okay, so that's cosine. So you can graph cosine lightly, make it dotted, make it light, make it light, make it light. You don't have to, but if you do, make sure it is very light, because that, what I've drawn right here, is not the graph of secant. Now, when we graph secant, make it red, they have the maximum in common. Again, the reciprocal of 1 is 1. Every point on the midline, there are 2 for cosine, and we're going to have a vertical asymptote. Now, when we graphed, the way I taught anyway, when we graphed cosine, we had 2 x-intercepts, or 2 points on the midline. So when you graph secant, minimally, you should have 2 vertical asymptotes. Okay? And then here's where it gets weird. If you only graphed what I graphed in orange, so let me erase this little extra here, and over here. Most of you are in the habit of only graphing this portion of cosine, which is fine. So when you graph secant, it's just going to look strange. So just know you're going to start here, and then you're going to blast up toward the vertical asymptote, because you had one full hump going, right? You had a turning point where the curve was decreasing and then increasing, you're going to have one full branch here. And then for this half of a hump, you're going to have another half of a branch. So you really have half of a branch, and one full branch. And that looks kind of weird. Okay, so for the vast majority of you guys who have been graphing this only for cosine, you're going to have what I have in red. It's going to look a little wonky. For those of you who have been graphing lots of waves, which is fine, keep doing that. Just make sure you put those 5x values for one full period. You're going to have a whole lot more vertical asymptotes and branches. So if you want, guys, for those of you who have been graphing what I graphed in orange, you can go ahead and just extend that branch, but you don't have to. Okay? So when you're done with secant, you're going to have what looks like, even if you draw it by hand, you're going to have what looks something like. So some of you have been doing this, and you have your midline. Okay? So when you're done, it'll look like what I'm about to do in red. Vertical asymptote. Vertical asymptote. One full branch here. And then here you're just going to draw a branch that approaches the... And here you're going to draw. So when you're done, you know what you did. But if somebody had never seen this before, they'd be looking at that like, I don't know if that's some kind of strange monster or you know, emoji, or I don't know what that is. But the red is the secant graph, and the orange was cosine, just as a guide. Okay, so make sure that that cosine portion is really light, dotted, grayed out. You erase it afterward, whatever. But just make sure it's not just all solid, and it just looks like some kind of mess. All right. I'm not picky about much, but I'm picky about that. All right, so let's do one example through and through just to kind of see how this process works. Okay, so if I give you a cosecant graph, you literally just rewrite the function. And for those of you that have been using colors, this is a good time to use colors. Choose a really light color for the sine or cosine, because that's just a guide, and then choose a bold or dark graph or dark color for cosecant. All right, so be careful because you don't see parentheses. Your argument is only x. So we're looking at sine of x times 2, that's my a value, minus 1 on the outside of the function, that is your negative 1 is your d value. Okay, so because your argument is x, so that we're going back now, we're going to graph one full period. Some of you have not been using this method, which is fine. I'm going to graph one full period. So our midline is negative 1. So I'm going to go ahead and throw that in there. The question was, in all classes, do we have to draw the midline? Absolutely not, but I like to draw it just so we can see that those are going to be, that's kind of my guiding line. So I'm down 1, starting at 0. So 0, down 1. So this is negative 1. This is positive 1, 2, 3. It's negative 2, negative 3. All right, so sine is going to go up, down, up. Now we're going from 0 to 2 pi. So 0 to 2 pi. Half of 2 pi is pi. 3 pi over 2. My hope is you've gotten pretty good at finding these exact x values. So remember, some of you are drawing tons of waves, which is beautiful, but make sure between one full wave you have 5 x values. You don't have to do it for the entire graph. Okay, so I have my 5x values. I have my midline of negative 1. A is 2. So now, and I'm graphing sine, and I'm doing it lightly, I'm going to go up 2 spaces, which takes me to 1, down, back down to the midline. So far I have 2 points on the midline, down to 2 spaces, which is actually a y value of -3, and then back up to the midline. So my hope is this is my sine graph, that you're like, got that. So this is all review. Everything in orange is review. Now, for today's lesson, which isn't much. Today's lesson is graph the reciprocal function and then invert it. All right, so we know for every point, 1, 2, 3 on the midline. So if you plug in 0, sine of 0 is 0. What's the reciprocal of 0? Skirt, undefined. Calculator says error. If you plug in pi, sine of pi, 0, the reciprocal, skirt, undefined. All right, so for every point on the midline, you can trust that the reciprocal function will be undefined. Okay? They have this maximum value in common. So if I plug pi over 2 into sine of pi over 2 is 1. 1 times 2 is 2. 2 minus 1 is 1. Cosecant of pi over 2, what's the reciprocal of 1? 1. 2 times 1 minus 1 is also 1. So you can actually see numerically that every maximum value is where sine of that value is 1, the reciprocal is 1. So these outputs, these y values are the same. But then after that, you have an inverse relationship. All right, it's hard to see that for 1 because the inverse of 1 is 1. So as your curve goes toward the midline, the reciprocal function blasts off to infinity. And then for every minimum value, they share that point in common. So that's really important that you have the hump of sine and the branch of cosecant touching at that maximum for sine and the minimum for sine, and then you blast off. Make sure you don't go through those asymptotes. Remember, that was a point loss opportunity. Don't let it happen. Make sure that your curve, your branch, does not touch the asymptote, that it approaches the asymptote. And that's it. So what I'm looking for is what's in red. I'm looking for every single point that you sketch that represents a point on the midline. There should be a vertical asymptote. And for every max or min, there should be a branch of your cosecant or secant function. All right, guys. Kind of short and sweet. To graph any secant function, make sure you graph cosine very light, very carefully and gently, and then be very bold with the inverse. To graph cosecant, graph the sine function gently and carefully and lightly and dotted or whatever you want to do, light color, and then graph cosecant bold. Look at that, 18 minutes, beautiful. All right, guys, good luck. You can now graph all 6 trig functions. Don't forget, 5 exact values for 1 full period of the graph labeled on the x-axis. Get your hundo.